Okay, so this is our second example. We want to solve this inequality here. This is 2x plus 3 times x minus 1 squared over x plus 5 squared is greater than or equal to 0. Okay, so how do we solve such an inequality? So if you remember last time we were solving polynomial inequalities, this is a rational inequality, right? When you have a fraction like this, it's going to have a numerator and a denominator, right? So we have our numerator. In fact, let's write it this way. Numerator n of x is just 2x plus 3 times x minus 1 quantity squared. And then the denominator, the d of x, if you will, is just x plus 5 squared. Right. Now notice that on the right side we already have 0. So it's already in one of these forms. In fact, it's in this form here because this is greater than or equal to 0. Right? So yeah, it's already in the correct form. So step one is, if it's not in this form, we have to rewrite it in that form. And sometimes that's not easy. Sometimes that's the hardest step here, actually. But we'll do one of those as well. So, right, so since it's in this form, our step two, right, so again, step one is done for us. And our step two is to solve p of x. Sorry, that should be n. I don't know why that's a p here. This should be n of x, and this should be d of x. So set the numerator equal to 0. And notice that it's already factored for us. So they were kind enough to write it in this factored form to make it easy to solve. So we just set the factors equal to 0. 2x plus 3 equals 0. That gives us x equals negative 3 over 2. And x minus 1 equals 0 gives us x equals 1. Of course, that's, you might think of that as a double root, or a 0 of multiplicity 2. Okay. All right. Next, we set the denominator equal to 0. So the denominator is just x plus 5. Right, oops, x plus 5 squared, that's a 5. So when you set that equal to 0, you can take the square root, subtract 5 from both sides, and we get negative 5, right? So there we go. We solved the numerator, we solved for the denominator, and so now we have step 2 is done, right? Step 3, right, and this is the same as in for when we did a polynomial. We're going to draw a number line, just a very long number line here. And we're going to mark off not just the two solutions from the numerator, right? Not just these numbers here. Although let's do that first, right? So we have negative 3 over 2, or negative 1.5. We have positive 1 over here. And now we also have negative 5, which is way over here somewhere, right? Because that's smaller than negative 1.5. So now we have 3 dividing points here, or what I call boundary points, or dividing points, on our number line, right? All right, so we're going to put a 0 at the point, be careful. So put a 0 at the points, but only, right, where the numerator is 0, right? So that's at 1 and negative 3 over 2, right? So that's where these are equal to 0. Let me use a different color here. Let me use red. So 1 and negative 3 over 2, that's where this function equals 0. But what about negative 5? At negative 5, the function does not equal 0. The denominator is 0. Remember, when the denominator is 0, that's bad. That means this function here, if you want to think of this as your f of x, right, the whole thing is going to be undefined at negative 5. Right, because it's in the denominator, and that would make the denominator 0. In other words, if you plug in negative 5, you get some number. Oh, let's calculate it, right? Negative 10 plus 3 is negative 7. Negative 7 times negative 6 squared. So 36 times 7. I can't do that in my head. I think it's negative 252. But it really doesn't matter because negative 252, because the denominator is 0, this is undefined. So we can't put a 0 here. I'm going to put a u for undefined, right? So at -5, the original function f of x is undefined. But when you plug in -3/2 or 1, you would just get 0, right? So if you plug in 1, this is 0. It's also what you get if you plug in -3/2. And you can check that. You just get 0. Okay, now what? So step 4, on each segment, pick an x, and then evaluate the original function. Again, I called it f of x. It's really just n/d, if you prefer, and determine its sign, right? So just like in the last example, we're going to have to pick a number that's less than -5. So I'm just going to go one less than that, -6, and we'll plug it into this function here. So this is going to be 2 times -6 plus 1 times -6 minus 1 squared, all divided by -6 plus 5 squared. And yep, that's a lot of arithmetic here. We get -12 plus 1 is -11 times -7 squared divided by -1 squared. So this is just going to be some big number, right? 11 times 49. I think we get in the numerator -539, and the -1 squared is 1. So it turns out it really doesn't matter what number this is. All we care about is it positive or negative. And I think it's pretty clear it's going to be negative, right? In fact, anything when you have a square is going to end up being positive. So it's just this number here, the -11, that determines the fact that this is negative, right? So what does that mean? It means that when x is -6, f of x, or n/d, is going to be negative. And so it's going to be negative everywhere less than -5, right? Okay, let's go on to pick a number between -5 and -3/2. So this is -1.5, so you can do -2, -3, or -4. I'll just do -4. Why not? So when you plug it into the original expression, you're going to get 2 times -4 is -8 plus, oops, this is a +3 here. I don't know why I was adding 1. All right, now I got to fix this. So -12 plus 3 is -9, not 11. So the -539 wasn't even correct. Yeah, what's 9 times 49? It's 441. So this should have been -441 here. Doesn't affect the outcome. It's still negative, right? But this should have been a +3, not a +1. So I don't know what I was thinking. All right. Anyways, 2 times -4 is -8, plus 3 is going to be -5, times -4 minus 1 squared, all over -4 plus 5 squared. And so this is going to be -5 times some positive number, right? It's just -5 squared over 1 squared. So I think we get -125. Sorry, not 12, 1 squared. 1 squared is 1. So 25 times -5 is -125. I think that's right. Either way, it's still negative, right? So that means here, this is still going to be negative everywhere between -5 and -3, which is that's where the -4 was from. All right, keep going. Plug in a number between -3/2 and 1. Well, I like 0. That's easy enough. So plug in 0. And I think we're just going to get 3 times -1 squared over 0 plus 5 is 5 squared. So we get 3 over 25. Right? Or if you prefer, 0.12. Either way, it's a decimal, it's a fraction, but it is a positive number. It is greater than 0. Okay, so that tells me that at 0, it's going to be positive. And it's going to be positive everywhere between -3/2 and 1. Again, we just happen to pick 0 because it's a nice number, but it's going to be true when x is 0.5 or -1.2 or whatever. Okay, All right, now we pick a number bigger than 1. So how about 2? Right? Just keep it simple, right? There's no reason to plug in, 793 just because it's bigger than 1, right? Keep it simple, and we'll just plug in 2 here into the original function. So we get, oh no, okay, I think I did that right. 2 times negative 4. So 2 times 2 is 4. 4 plus 3 is 7. And then 2 minus 1 is 1. 1 squared is 1. Divided by 2 plus 5 is 7. 7 squared is 49. So 7 over 49 is 1 over 7. And that, I think, is positive, right? There's no negative numbers here anyway. So that tells me that at 2, the function f of x, rather, is positive, and it's going to be positive everywhere bigger than 2. Okay. All right. So that should answer the question. Well, I'm sorry, that's step 4, right? So now we're almost done. We marked each of these places on the number line with a plus or a minus, depending on what we got here for our answers in step 4. And now we just need to write the answer using interval notation, right? So that's the fun part here. So in the original problem, right, we wanted to solve f of x, right? So I'll call this step 5 here. F of x is going to be greater than or equal to 0. Where is it greater than or equal to 0? Well, it's going to be greater than 0 everywhere between -3 and +1. And everywhere between, or I should say, or everywhere between everything bigger than 1, right? So that just keeps going forever. And so, yep, so that's where it's greater than 0. Where does it equal 0? It equals 0 here at -3 over 2 and at 1 as well. So in fact, we're not skipping over any numbers here, right? We're not skipping over anything. We're just starting at -3 over 2. And we keep going on forever. For that symbol, we use the infinity. Remember, infinity is not a number, so it never gets a bracket. It's a parentheses. And so I think that's the solution set, right? We don't want where it's negative. We don't want any of these numbers here, right? So we don't want to include any of these, or where it's undefined, or where it's negative. So none of these are going to be solutions, but these will be. So I hope that helps. So that's what happens when you have an example of a rational expression. You have to worry about not just where the numerator is 0, but also where the denominator is 0. So that's an example, or that's another example here. And I think I'll do one more example, and I'll make it one of the more difficult ones where you don't just have 0 on the right already. Okay, so one last example. We want to solve this inequality here. And this is going to be probably one of the harder ones. We have x plus 2 over x minus 1 is greater than x plus 3 over x plus 1. So just to make it clear, right, we want to solve the following inequality. X plus 2 over x minus 1 is strictly greater than x plus 3 over x plus 1, right? So why is this one going to be difficult? Because this does not equal 0. And if you remember, going back to our chart here, we have to have 0 on the right side, right? Before we do anything else here, we have to get this into the correct form. This has to equal 0, which means we have no choice. We have to actually subtract this from both sides, right? So we're going to actually subtract, right, this whole expression, x plus 3 over x plus 1, from both sides, right? And what we end up with is, all right, so this is all just step 1 here. We end up with x plus 2 over x minus 1 minus x plus 3 over x plus 1. Now, how do we subtract, I'm sorry, this is greater than 0, right? Because, yep, all of this just adds up to 0 now, right? Okay, so now we have this on the left side. On the other hand, this is not a single fraction. This is 2 fractions, right? So we have to subtract these. And now we have to remember, well, how do you subtract fractions? Well, you subtract the numerators if the denominators are equal. X minus 1 and x plus 1 are not the same thing. So this is going to take a while here, right? We have to do x plus 2 over x minus 1, leave some space here, minus x plus 3 over x plus 1. So in order to subtract these two fractions, we need to find, if you remember, the least common denominator, the LCD. So what are the denominators? Well, we have x minus 1 and we have x plus 1. Luckily, that's all we have. So the least common denominator, just take their product, multiply them together, and that'll form the least common denominator. Okay. Now we have another problem though, right? Because this denominator here, and I should include parentheses around everything. Yeah. All right. So those are just parentheses. So notice that this denominator is x minus 1. What are we missing? We're missing x plus 1. So I'm going to have to multiply numerator and denominator by the missing factor, x plus 1. For the second fraction, we have the x plus 1. Oops, that should be a plus here, right? X plus 1. We're missing the x minus 1. So here it's the opposite. I have to multiply numerator and denominator by x minus 1. Okay. All right. Now, what is all this equal to? So now we have the same denominator. Oh, they're in the wrong order. They're in the opposite order, but that doesn't really matter here. I'll just pick the first order, x minus 1 times x plus 1. Remember, you're allowed to change the order. All right, but in the numerator, well, we have this giant mess. We have x plus 2 times x plus 1 minus x plus 3 times x minus 1. Unlike the denominator, we got to expand this out. We have to multiply all this out. Right? So yes, I know this is a lot of algebra, but that's what it takes. That's what we got to do here. So if we FOIL the numerator here, we have x times x is x squared. Then we have 1x plus 2x is 3x. And then 2 times 1 is 2. So that's, right, I'm just using FOIL. And do the same thing here. But here you got to be careful because there's a minus sign. So we're going to subtract the whole thing here. So again, x times x is x squared. And then we have negative 1x plus 3x is positive 2x, I think. And then 3 times negative 1 is negative 3. Okay. Leave the denominator alone. This is just x minus 1 times x plus 1. You'll see later why there's no reason to multiply that out, right? Obviously, it's just x squared minus 1, but we don't need to write it that way. Okay, so let's keep going here, right? We can distribute this negative sign here. And for the numerator now, let's keep the x squared plus 3x plus 2, and then subtract x squared, subtract the 2x, and then subtract negative 3. Well, that's just adding 3, right? And leave the denominator alone. That's a plus. Right. So now, notice that in the numerator, we have x squared minus x squared. Well, that's just 0. So that's nice. We also have 3x minus 2x. Oops, minus 2x. 3x minus 2x is just x. Oh, I might need the space later here, so let's write it down here. This is just x. And then finally, 2 plus 3 is 5. So x plus 5 for the numerator. And then the denominator, leave it alone. X plus 1, x minus 1. Doesn't matter the order, but I'll keep the same order. X minus 1 times x plus 1. All right. So that, oops, I didn't mean to cross anything out here. I'm just highlighting our final results, and believe it or not, this was all just step 1. Oops, sorry, right in the above form. So what we did here is we wrote this, right, in the form where we have a function, right? We have a numerator and denominator, and that was equal to, oh, I forgot, x plus 5. Sorry. So the numerator was x plus 5, and the denominator was x minus 1 times x plus 1. Okay. Yeah. That was just step 1. We're not even close. We're not even halfway done, right? Again, that's because this was in a particularly nasty form in such a way that we had to get 0 on the right, and then we had to combine these, subtract these two fractions in order to get a single fractions, in order to get one numerator and one denominator. All right, remember, that is going to be greater than 0, so this is greater than 0, right? And now we move on to step 2. Step 2. And what was step 2? Yeah. So step 2 is to set the numerator and denominator equal to 0. If you forgot, you can scroll up here, but yeah, set the numerator and denominator equal to 0. So setting the numerator equal to 0, x plus 5 equals 0, well, that just gives us x equals negative 5, right? Setting the denominator equal to 0, and this is why we left it factored, we just get x minus 1 equals 0, or x equals 1, and x plus 1 equals 0 gives us x equals negative 1. So I should have written them here, sorry. X equals 1 and x equals negative 1. All right, good enough, right? So we have 3 solutions, 1 from the numerator and 2 from the denominator, right? So what's our step 3 now? Step 3 is to draw a number line. Here's the number line. And mark off all these solutions here. So we have a negative 5 way over here. We have a negative 1 somewhere over here. And then we have 1 somewhere over here. I mean, they don't have to be, you know, obviously there should be more space over here, but we don't need to worry about that. Just as long as you mark the 3 numbers on the number line here, right? And now notice the numerator is 0 when x is negative 5. So here the function f of x is going to equal 0. But when x is either 1 or negative 1, that's when the denominator is 0. So that's when the original function is undefined. So U for undefined. Okay. Now we just fill in the signs here. Plus, minus, plus, minus. Well, yeah, I don't know what they are yet, right? But let's do that by the same thing we did before. Pick your favorite number less than negative 5. I like negative 6. And plug it into this function here. So plug it into the simplified version, right? We get negative 6 plus 5 over negative 6 minus 1 is negative 7. And then negative 6 plus 1 is negative 5. So we get negative 1 over 35, which is negative. And that means that when x is negative 6, or anywhere x is less than negative 5, the function will be negative. Okay. So rather than just plug these in here, let's look at the form of the numerator here. The numerator is x plus 5 to the 1. The denominator is x minus 1 to the 1, and x plus 1 to the 1. Notice all the exponents here are 1s. And 1 is an odd number. When the number is odd, what happens is that the sign just switches. So at negative 5, because the exponent is a 1, and not a 2 or a 4 or a 6, right? It's an odd number. That means the sign switch. So here it's going to be positive, right? Right. Now, if you don't believe me, well, then pick your favorite number between negative 5 and negative 1. I like negative 2. So let's plug that in. We get negative 2 plus 5 divided by negative 2 minus 1 is negative 3. Negative 2 plus 1 is negative 1. So we're going to get 3 divided by 1, which is 3. And 3 is a positive number. So I told you, sorry, I don't mean to put minus signs there. I mean to highlight the fact that this was bound to be a positive, right? So what's between negative 1 and 1? Well, 0 is a good one, so we can plug in 0 here, right? On the other hand, right, we know that at negative 1, right, that comes from the x plus 1. The exponent here was also 1, and so we expect the sign to flip again, So we expect this to be now a negative here. And so whatever number you get here should be negative. Well, we can figure it out pretty easily. It's going to be 5 divided by negative 1. So it's going to be a negative 5. As promised, it is negative. So what happens when you're bigger than 1? Well, we expect the sign to flip again. We know that because this exponent here, right, coming from the x, remember, x equals 1 came from x minus 1. So that factor also has an odd exponent. And so the result is that these signs should flip and become positive. So what happens if you get an exponent of 2? It means the signs do not flip. They stay the same, right? If you get an exponent of 4 or 6 or any even exponent, that's when the signs stay the same, rather, right? Okay, so, right, but just to make sure, right, pick your favorite number bigger than 1, say 2, and plug that in. You're going to get 2 plus 5 is 7, divided by 2 minus 1 is 1, and 2 plus 1 is 3. You get 7 over 3, which is indeed positive, and that's why we get positive numbers here. So this saves you a little bit of work of having to plug in all these numbers here. You do have to plug in one number because you know that because all the exponents are odd, all the signs flip. But how do you know they didn't flip from, say, positive to negative, positive, negative? Because that's the opposite. Here it's negative, positive, negative, positive. So you have to plug in one number somewhere. I just happen to pick the one way over here on the left. Once you determine those signs, you can determine all the other signs just by basing it on the evenness or oddness of the corresponding exponents. Right? And we could have done that in the previous example. If I can go back to the previous example here, notice that in step 4, we spent a lot of time calculating all these numbers, and you can see I messed up some of the arithmetic here. But the easiest way to do it is once you plug in negative 6, right? And again, that's a coincidence, negative 6, right? But once you plug in negative 6, we determined that it's negative here. And you better make sure that's correct, because if you get that wrong, you're going to get all the signs wrong, right? But I'm pretty sure when we plugged that in, we did get a negative value for y, right? We got negative 441. And so because of that, these signs were negative. Now, what happens at negative 5? Well, where does the negative 5 come from? It comes from, over here, the factor x plus 5 squared. So notice the exponent here is 2. 2 is an even number, so that means we expect at negative 5 the signs not to flip. They stay the same. They stay negative. Okay? Notice that? Right. Now, if they're negative to the left, what happens to the right of this negative 3 over 2? So where does the negative 3 over 2 come from? That came from this. That came from the 2x plus 3 to the power 1. Well, 1 is an odd number. 1 is an odd exponent. So since we have an odd exponent, at negative 3 over 2, we expect the signs to switch, to flip from negative to positive, and they do. What happens at x equals 1? At x equals 1, that came from the x minus 1, and the x minus 1 had a power of 2, which is even. Even means they stay the same. So the signs did not flip at 1. They stayed positive to positive. So we could have done that here, saved us a little bit of work. But now you know that you can look at the multiplicities, right, or the exponents of the corresponding factors to determine whether the signs flip. All the signs flip here, right? Negative, positive, negative, positive. Just realize that that doesn't always happen. And that doesn't happen, of course, when the exponents, when you have, say, 2s or 3s for exponents, right? Well, actually 3 would also flip because 3 is odd, just like 1 is, right? Just like 1. But 2 or 4 or 6, when those are the exponents, then the signs don't flip. They stay the same. Okay, in any case, that was step 4 already, so we're almost done here. Step 4 was to calculate all the values, and in fact, you don't have to do that. You can just go by the multiplicities, go by the exponents. And then for step 5, you're filling in whether these are negative or positive. So all that's left to do in step 5 now is to actually answer the question, which was what? It's to solve this original inequality here, right? On the other hand, we converted that to this inequality here. It's the same inequality, just written differently. And remember, this is greater than 0. Greater than 0 means positive. So where is this positive? These are positive signs, so everywhere between -3 and -1. And it's also going to be positive everywhere bigger than 1. Right? And this just keeps going. Okay, so we're including at least these intervals. Are we including anything else? Notice this is not greater than or equal to 0, right? So there's no equal sign. So that means we're not including where this equals 0 here. We're not including the -5 here. Okay, so we're not including -5. So this is, if you will, this is going to be an open circle here at -5. Do we include the -1? Well, that has nothing to do with this not being equals. It has to do with the fact that there's a u here. It's undefined. So whenever you have a u, you never include that. That will also be an open circle. And the same thing happens at +1. It's an open circle here, right? So remember, open circles are where we do not include the endpoints. So in fact, we don't include any endpoints here. So these are all going to be parentheses, right? So our solution should be, everywhere we're highlighting, we're going from -5 to -1 using parentheses, right? We skip over -1 to +1, and we join the union with this interval from 1 to infinity, but not including the 1, right? So parentheses. So that's our final answer. That's the interval notation for the solution set for this example here. So I hope that helps. I know this was a long one. In particular, half the problem was just doing all the algebra here to get the answer we needed here in the proper form. Because remember, the first step, it has to be 0 on the right side and a single fraction on the left. So that was a lot of algebra just for step 1. And that's what made this a pretty difficult problem. Right, and if you remember in the first example here, it was already greater than or equal to 0. And in fact, this was already a single fraction, and it was already factored for us. So this example here, I would call this not an easy example, but a routine one. It's one that a fairly standard example where the hard part was figuring out the signs, whether it's negative or positive, and then to get the interval notation. The hard part was not the algebra. There really wasn't much algebra here. It was already simplified. We just had to, set the factors equal to 0 and solve. But in this problem here, because we didn't get 0 on the right, we had to subtract that from both sides and then combine these into a single fraction. And as you can see, that was a lot of algebra here. But in this case, it was necessary. We had to do it that way. So I hope this helps. Again, this is done a little differently than the book. The book uses sign charts to get the negative and positive signs. You can do it that way if that's what you're comfortable with. I call this a sign chart as well, but it's really just a number line where the values of this function, the original function up here, whether they were positive or negative at each value of x. So I hope that helps.